Hey there, welcome back class. If you check out today's notes up on the board, this is just a quick recap of where we went today and where we're going down the line. If you saw yesterday's, you didn't have to take notes on yesterday's, but it was kind of a good recap on what we've been doing in our first 10 pages of our book. Remember, there's no homework that's due this week. All the graded stuff starts next week, week number 2. So if you look at where we started off with today, current events. We did our 5-minute of current events. Yes, the show lasts 10 minutes and you can watch the whole thing. I totally encourage you to watch CNN 10 on your own. But we only use the parts that are germane to the class. We don't even use CNN 10 all the time, but this one was germane to the class. They are hoping, they being NASA, are hoping to launch pretty soon a satellite, a space telescope that's able to capture or at least collect enough light to see rogue planets. Now, rogue planets, like Carl Azuz says, sounds like something out of Star Wars. That's the lightsaber. If you check out rogue planets, they're planets that are not orbiting a star. Like obviously we go around the sun, we orbit our sun. There are planets out there that don't orbit stars, we think, and they're going through the galaxy unaccompanied. That's really difficult to see because one of the things we've been doing this week, hopefully, is checking out our moon, looking at our moon observations. And when we look at our moon observation right now, you only see the moon, of course, because it reflects light from the sun. The moon doesn't put out any visible light that we can detect. So when you're looking at the moon, you're looking at reflected sunlight. If you have a planet that is interstellar, between stars, interstellar, you've got a planet that has no light that it's putting out itself and wouldn't be close enough to a star really to reflect very much light, probably. And so it's really difficult to detect. We talk about that a little bit more in detail when we do a little bit of astronomy. So that's where we're going outside of the book there a little bit with current events. We started with our notes today on atoms and temperature. Again, goes outside of our textbook a little bit. Our textbook is a good guide, but it doesn't really address everything in the NGSS, the new science standards. So we just want to make sure that we're touching on things that we need to really understand. Viruses, for example, this year is cells. And one of the things our book does a wonderful job of is go through the systems, human body systems, how cells work, things like that. One thing that it needs to touch on just a little bit is atoms and molecules. And if you look at the atom, what is an atom? You see it says the smallest piece of matter. The idea behind an atom was basically this. If you could take something and break it and break it and break it again. There was a Greek philosopher, a guy by the name of Democritus, you didn't have to take his name down, had the idea that you would eventually get to the part where you couldn't break it apart anymore. It was unbreak-apartable, as Bill Nye once said it in one of his videos. The idea behind that was you would reach the point of being an atom. Now, it turns out that, yes, there are particles smaller than an atom. You break an atom apart, if you have a nuclear reaction, you've got protons, neutrons, electrons, quarks, and electrons will be important later, protons, neutrons will be important later, the things on the inside of an atom. But when you look at an atom itself, there's about roughly 100 naturally occurring in nature. If you look at the periodic table, there's 92 naturally occurring. We can make some in the lab. They fall apart very, very quickly. So, are they real elements or are they not? They are only stable for, in many cases, fractions of a second. But the point is this. You can think of atoms almost like little Legos in nature. I use Legos as an example. I'm looking around for my Lego ship, this particular ship, built with my son a little while ago. This is just the box for it. But we've all at one point or another played with Legos. You can see all the little pieces that get put together. In nature, there's basically 100 different types of Legos with which to work. And those Legos we call atoms. The atoms combine, fortunately for us, to make molecules. And this one was circled here because it was the most important note of the day. Atoms and molecules are always moving. There is no place or situation in nature that we can think of where they do not move. We'll talk a little bit about that, but the science of studying the movement is temperature. If you look at a thermometer here, for example, you're measuring temperature. What you're really measuring is the kinetic energy, the movement of atoms and molecules. The example that we did, the home experiment or activity that we did today was basically just this. I'm walking up past the camera and I'm getting my glass of water and a little bit of food dye. And we took just a little bit of dye, or if you didn't have dye available, you could dip in a felt pen, and we did a drop in there. Now, apart from the, whoa, dude, looks like a lava lamp. Apart from that and enjoying the slow mixing of the dye in the water, I challenge the student, I want you to think about it in terms of atoms and molecules. Could you think of a situation where if we put the dye in very, very delicately, we left this classroom for the weekend, there was no air currents in here, everything was perfectly still, could you get to a situation where that dye would not mix? And if you think about the previous note, atoms and molecules are always moving. No matter what you did, it would eventually mix. Even if this was solid ice, it would still eventually mix all the way through it. How is that possible? Well, if they're always moving, the atoms and molecules, and we'll talk a little bit about Brownian motion later, you'll see it in the book, but the atoms and molecules are always circulating, they're always moving. Later on, we use this as an example of pollution in our environment. You can't just say, well, we're just polluting in this one spot, but we're keeping it here. It doesn't work like that. The water cycle, the biogeochemical cycles are bringing everything around this contained area that we call our biosphere, our Earth. How do we measure the movement of molecules? Again, temperature. 3 scales here we have to talk about. One is Fahrenheit. Yeah, sorry, not to bag on our country too much, but why can't we get together and go with Celsius like the rest of the world does? It's complicated. So on behalf of my generation, I'd like to apologize for you students out there that have to learn the 3 temperature scales instead of just 2 like it should be. We use Fahrenheit. You turn it on the news tonight, if you check out, it's 66 degrees outside here right now. That's 19 Fahrenheit. Anywhere else in the world, they say, well, it's 19 degrees here in Pacifica. Here, if you check out the news, it's going to say 66 degrees. Fahrenheit is a little bit outdated. Almost no countries use it anymore, but we do. So we have to know a little bit about Fahrenheit, and that when you're measuring kinetic energy, temperature, in Fahrenheit, 212 is boiling for water, 32 is freezing for water. The much easier scale to use is Celsius. Why? Easier to remember, metric system, based on 0 being the freezing point of water, and 100 being the boiling point of water. Nice and easy to remember there. You get to 0, you're freezing, 100, you're boiling. And the Kelvin scale over here, Kelvin scale is not used in everyday activity. Right now here in Pacifica, it would be about 290 Kelvin. Doesn't really make it a practical system to use on a daily basis. And so what you end up doing is using this in detail in scientific experiments. When you get to 0 degrees Kelvin, you get to a very special point. It's called absolute zero. The temperature scales have, theoretically no upper limit, but they do have a lower limit. And that lower limit is 0 Kelvin. 0 Kelvin, absolute zero, means all molecular motion, all motion of particles has stopped. There's nowhere in nature, there's nowhere artificially that we can make this happen, that does happen, but it's one of those things that you have as your starting point, and every other temperature is a going up as a measure of how much the atoms, the molecules are moving. On the other board today, which I don't think I'll pull over right now because we'll just wrap this one up, we just asked the students to write down their observations on the dye going through the water, on the dye circulating through the water. You can already see right now, and I'll take it very gently over here. Hey, it's still moving around. There's still places where it hasn't mixed in all the way yet. Chapter 1, pages 1 to 10, starts talking about solutions. With the dye in the water, you just made yourself a solution. The homework, which is still posted over there, is our moon observation, our readings, pages 1 to 10. And then finally, there's a few questions there on page 10 I'd like you to answer. I'll link those down below, and those will be out on your Google Classroom as well. Have a great day, everybody. We're going to go through a little bit more of this tomorrow. And again, look for your notes on Google Classroom. Down below, I'll try and make sure I link them, and then also on the blog. Take care. Have a good Thursday.